Bharti with Vilas Sarkar. Now we'll move on to problem number 47 in fluid statistics. The 47 problem says a cork is submerged in water by a spring attached to the bottom of a bowl. Attached to the bottom of a ball. When the ball is kept in an elevator moving with an acceleration downwards, what would happen to the spring? Okay, so let be a cork is submerged in water by a spring attached. So if I want to draw, let's say this is the data, the ground of the lift on which a bowl is kept, which is filled with water. An arrangement, a spring is there which is attached to a cork, okay, and this is filled with water. So now if it is the first case, when the lift is not moving, let's say, now this is the condition. So if I draw the free body diagram of the cork, so cork is there. What are the forces acting on the cork? The spring is pulling it, so there is a tension or the pulling force due to the spring on the block having its own weight W, and the buoyant force is acting upward. So if I equalize this, T plus W will be the B. Now what is T? Let's say this having spring constant K. So, and due to this arrangement there is a deflection of x1. So tension, the equivalent amount of the tension that is created on the spring, that with the same pull force is pulling the cork, it is K into x1. We know that the spring, the tension in the spring is equal to the spring constant into the deflection. This is the formula for spring, and the weight is equal to nothing but the volume of the cork into the rho of the cork into the G. Okay, the mass into the gravity. This also can be written as this, if I multiply volume with specific density to reduce the number of terms. Okay, buoyant is equal to the volume of the water displaced. This must be equal to the volume of the cork, because there is no change, because this is completely submerged. Volume water is volume of the cork displaced into the rho of water into G. So instead of that, we'll write it the specific density of water to reduce the terms. This is the first case. This is first equation. Now when it is moving with the acceleration a, that lift, so due to the inertia, everything which is not physically fixed will try to move with acceleration a on the, or at least he has to keep its inertia. Due to that, it will experience an acceleration opposite direction to the direction of the lift moving. So now moving, the elevator is moving downward. So acceleration must be there downward. The other acceleration that the system will experience will upward. So as this also. So now this is the first case free body diagram. The second case free body diagram will be when it is moving with the acceleration up a system. So this is the free body diagram. If I draw it, this is the cork again. The buoyant force will be different. The tension here is the tension created, maybe the T1 different, but the weight of the cork will not change because we are on earth, and whatever the gravitational force attracting anybody, it will be same. So this second case, my equation is the tension spring due to the difference of the buoyant force to the weight, and the weight will be same, buoyant force will be V1. Now T is equal to K, spring constant is a constant, so it will not change. Let's say this is the deflection in the spring, whether it's more or less I will decide later. Now weight is equal to volume of the cord, it's not changing, density of the cord not changing, same. Buoyancy, volume of the cord not changing, this it will displace the same amount of water to water, and buoyant force here. Now this term basically is rho into G. So in this case, that buoyant force G is nothing but G effective. This is the concept that I already described while I was discussing about some accelerated on the accelerated body, some liquid is being kept, and what would be the effect. Okay, so this is for buoyant force rho of water here and into the G effective. So G effective for first case when there is no acceleration, so G effective is equivalent to G for first equation. For second equation, G effective is equal to G, that is downward, minus that A on the body, G is acting downward and A is acting upward. So G effective is G minus A. This is the only change for second case. So for this case, I will better write volume of cork, rho of water, and G. In second case, this has to be rho of water same, but G will be G minus A. So this is the thing is changing, G effective. Okay. So now this is my second equation. So deduct, this is my first equation. So if I deduct, so I have to take some part of the board. So I will rub it out. 1 minus 2 if I do. So 1 minus, this is 1 minus 2. So what will remain? K into x1 minus x2. This part is same. It will go out of the equation when I do 1 minus 2. And this is Vc and W is common. So I will take it common. Rho W means density of water. And this will become G. And this will take the sign change and A. So this will be cancelled out. So ultimately this will become x1 minus x2 if I keep one side. The other thing I will keep on the other side, rho of W into A divided by K. Okay. So now this is positive, volume cannot be negative, rho cannot be negative, acceleration I am taking as a positive because downward it has some value, and k is also positive. So this all together is greater than 0. So x1 minus x2 is greater than 0. So that means x1 is greater than x2. So that means on the other side, other way, x2 is less than x1. So that means whatever deflection for the first element, when there is no acceleration, the deflection is x1 is more than x2. So in second case, when accelerated, the deflection in the spring will come down. So that means the length of the spring, my answer will be, what would happen to the spring? Length will reduce. The length of the spring will reduce due to this effect. Understood? Okay. So moving to the next problem, that is problem number 48. Says a body is just floating on the surface. A body is just floating on the surface of a liquid, on the surface of a liquid. The density of the body is same as that of the liquid. The body is slightly pushed down what happened to the body? What will happen to the body? So what it says, a body is just floating on the surface of the liquid. So if I say this is an arrangement where the liquid is taken, a body is just floating on the surface of the liquid. So that means the body is somewhere here. It is floating just on the surface of the liquid, like that. Okay. The density of the body is same as that of the liquid. So if the density of this body is B, density of the liquid is F, so rho V is equal to rho of F. So now the floating, the principle of flotation of principle is weight of the body is equal to the buoyant force. That has to be, there is no imbalance in between this force. The weight of the body is the volume of the body into rho of the body, and if it is the buoyant force is the volume of the liquid dispersed. Now the body is just floating on the surface. That means body should not be here. Body is floating. It is floating like that on the surface, means just on the surface, touching on the surface. So that means unless and until that is dispersing some water, there is no chance of buoyant force. Only the pressure will act, but pressure is not creating. So that body is just floating on the surface, is not practically happening. Some part of the body must be below the water. So if it is floating on the surface, that means it is just on the surface. It has to be understood like that. The body is just floating on the surface. That means on the surface means the touching the surface. This has to be the case, because other earlier case what I have drawn there, no meaning is coming, because if I do equal, so this V, if it is on the, that is not dispersing, so this will be 0. So the buoyant force is 0, weight cannot be managed by any other force is not there. So this would not be the case, rather it is the top of the body has to be matching the surface. This should be the case. So weight of the body is rho V, volume of the body. This is, and this is volume of the water dispersed. If it is just floating, so this is equivalent to the this is not water, the volume fluid dispersed, rho of the fluid. Now this is equal to this, so this must be equal to this. So this is the flotation when body is just on the surface. So this is the case when the volume will be equal and the density, because from the understanding when it is just in, this can be equalized. This, even if it is not said from the principle, we can prove it is same. So this is already said. So in this case, this and this are same. Now there is no residue force which will move it up or down. Now a force is being acted on it from top. Any force, any little bit of force. So this force is a imbalance in the system. So how it is imbalance? This force is, the way it is being acted, it will give some imbalance, and due to that it will get some acceleration. The force is mass into acceleration. This has some mass and it will get accelerated due to this imbalance force, because once it's down, there is no other thing which will restrict this force. This force is acted. Now this will move on, because this is the imbalance, because there is no other force. If I say there is no other force, because W and B, this part is 0. That's why it's just floating. So this part is 0. The total force acting on this F, mass into acceleration into, this will be the case. So this will go on moving unless and until this being restricted and hit the deck. So this will stop there, and then this solid surface will stop it to move further. Until then it will move, because this force is not balanced by anything, because we are talking about the ideal fluid, and ideal fluid there is no friction in that, so this is not considered. So this is happening. Okay. You can, even after, if you consider the, at any point of time the body is there, this is H rho G, the pressure, and this pressure is acting from both sides. So there is no even pressure energy into area, that means the force, because the force of the block, it will not acting on this. This is acting on the every direction. Okay. So now the body, the dimension is not there, but even if it is said, the force, if it is being to be considered due to the height of these two dimension, if it is so large, so there could be happen the force acting there due to the pressure energy on this surface, and force acting, because this will be nullified. What is the force acting on this, and the total force acting here due to the height difference, if it is say H L into rho into G, this could be the case that could reduce the effect of the force at some point of time. But this is a body, the dimension is not so clear, so you can think of a small body. Okay, if it is a body of a bigger dimension, so there could be possibility that the pressure energy increasing due to the height difference at any point of time. This force may at point of time, this may, but even though you can understand that if it is the force acting, the resultant force in between the surfaces is L rho g. This will be the same always because L is constant, rho is constant, and g is constant. Now this force, if is able to move it, so that means it is overcoming this force and then it is trying to move. So at any point of time, this force also not increasing, and this force also, the force is already given, that is not being reduced. If it is able to move this force is, even though it is at the surface of the fluid, it is having the same difference of pressure, this force, because this is same, so this is constant. In this point of time, the point, if I say this is the place number 1, the force is being countered by this force, so this is overcoming and putting force. And now if this any force which overcome this and able to move it, it will not a hindrance later on also, because that force is not changing, so it will move and hit the deck. This will be the condition if it is the body is slightly pushed down, and this push has to be somewhat which can overcome this force, that pressure energy of the liquid. So that is, anyhow, it is the buoyant force. This buoyant force is being equalized by the weight. That's why it is floating. So that means this effect, this is equivalent to the buoyant force. So the buoyant force already being countered by W as it is floating by taking the surface. So this effect will not come even if it is a slightest force. This, because this force is noded to overcome this force. This force is already overcome by the weight. So this thing is not coming in picture. Only thing, any force acting, it is a imbalance force, and that will create a motion into the body, and it will stop at the deck when it is being restricted by the surface of the liquid. Okay, so this will be the case. Moving to the next problem, that is problem number 49. A cubical block is floating in a liquid with half its volume, immersed in the liquid. When the whole system accelerated upwards with g by 3 the fraction of volume immersed in the liquid will be how much? Okay, so let me draw the diagram. So there is a cubical object. It is a layer of the liquid floating in a liquid with half its volume. So that means if it is cubical, the any dimension you take, so all dimensions as it is cube having the all three dimensions are equal. So in any way if you see, it will be the half of its dimension, its depth. So the volume will also be same. So as it is floating, for first case, what is the case? W is equal to buoyancy. That is the case. Okay. So W is equal to the volume of the block, of the cubical block, into the rho. G is not at all is coming, immersed in the liquid. So this is the block density, and V is the volume is V by 2, as it is half submerged, immersed, half of the volume, so V by 2 into the rho of the fluid. So from there we can directly calculate that the rho of F fluid is equal to twice of block. So this is the first equation. In the second case, when it is moved down with some acceleration, let's say A, that I will put later on the value of it. So that means the other things inside is moving in A, so as of the block also with A. So in the second case, the equation would be the W is equal to the, this is W downward. It is when the whole system is accelerated G by the fraction of volume. So that means the weight is balanced by the new buoyant force. Okay. So W is a B1. So W is equal to B. But that is having the new buoyant force. So the B is equal to B1. Anyhow, buoyancy will be same, but effectiveness will reduce, as because this is V into rho of, this will be the same, but here the volume dispersed, the fluid dispersed by the volume, this will little bit maybe go up due to the reduction in acceleration, and your the rho of the fluid will be there, and G here, one thing is that weight is multiplied by there, the first I have to see. So the real equation, G will be the both side, so G is cancelled out because W is equal to volume into density into G. Here volume into density into G, as G is same for buoyancy also, the effective G is here equal to G. As I said in the earlier problem, the effective J, unless and until it is being, the system is accelerated somewhere, so this G effective is equal to G. But the second case, this is not the case. Although the real equation is weight is balanced with the buoyant force, and as because it is in equilibrium, after getting accelerated, it will be same as it is. There could be some changes. This volume, whatever is submerged, may not be the same, that will change, but after change it will be in equilibrium. So the volume of the block, density of the block into G is the gravitational force acting on the block, because weight is not differed, as because we are in the same zone. So the buoyant force is affected by the volume. Now in this case the volume will change, whatever the displacement of liquid will change, not as the V by 2 into rho of the fluid into G effective. G effective, it is G minus A. Effective is G is downward and A is upward. So this is the effective G. So this case V1 is equal to that rho of F is equal to 2 rho of B. So I can put this value V1 into 2 of rho of B, you can put G minus A. This will be the case. So this will be cancelled out. So ultimately this will become V into G is equal to V1 into 2V1 into G minus A. So I am taking it this side. So V1 is equal to V into G divided by 2 into G minus A. So this will be equal to somehow half into V into, we can put 1 upon 1 minus A by G. So now A is equal to what? This is V by 2. I'm stretching it too much. So instead of that, this is V into G and 2 into G minus A is equal to how much? G by 3. Acceleration G by 3 if I put, this will be the 2G by 3. So V by 2 into 3 will go up, 2 will be there into G by G, because below is G minus G by 3, that is equal to 2 by 3 G. 2 by 3 will go up. So this will be G will be cancelled out. This will be 3V by 4. This much volume. So earlier it is V by 2, now it is 3V by 4. So that means there is a reduction in volume, so that that block will go up a bit. Okay, that the volume that is submerged, it will reduce due to the acceleration. So the new volume will be 3V by 4 amount. Okay. The next is number 50. Number 50. A hemispherical ball just floats without sinking in a liquid or else I will continue, because two more problems need to be shown. So I will club it in the next session, and along with that I will start, because this could be a very lengthy one. So people may not be interested in seeing the longer videos. So I will end up here. In the next video I will finish it off there, because as I doing 50th problem every time, so this only one problem is pending. So I will do it in the next class. Along with, I will start the theory part of fluid dynamics. Okay, so I will end up here. So thank you for now.